Today I will teach you about the thermal conductivity practical, right? Okay, so now on your right hand side it shows the apparatus, right? On your left hand side it shows the internal arrangement of the apparatus, right? So basically thermal conductivity is referred as the ability to conduct heat in solid materials, right? Using this equipment we are going to evaluate the thermal conductivity of two different materials, right? So one material is stainless steel and the other material is aluminium, right? So basically this equipment, and that means if you're going to consider the internal arrangement of this equipment, right, that means like here you can see these that cover is there, right? So there's a cylindrical cover, right? So if you remove that cylindrical cover, so you can see some sort of an arrangement as shown in the left hand side, right? So now basically uh, there are several types of this thermal conductivity apparatus, right? So certain types of apparatus are there where the two materials are actually one is copper and the other one is stainless steel, right? And if you're going to consider this diagram, here the two materials are one material is aluminum and the other material is stainless, right? Okay, so now if you're going to consider the structure of this arrangement, right? So now here you can see there is an electric heater that is placed on top of the aluminum material, right? So on top of the aluminum material we have the electric heater, and there is another thing that actually before doing this practical we don't know which material is having the highest thermal conductivity, right? So as you know that thermal conductivity is measured in watts per meters per Kelvin, right? So before doing this practical we don't know which material is having the highest thermal conductivity, right? But here you can see one thing, that electric heat, right, the heat source is actually closer to the aluminum material. So now in this practical you better carefully focus that this heat source, which is the electric heater, is actually closer to the aluminum material, right? Because the heat source electric heater is actually placed on top of the aluminum material, right? So now when the heat transfer is taking place away from the heat source, right, and if you're going to consider the temperature at points, right, that are actually closer to the electric heater, right, the temperature at such points is having a higher value when compared to the temperature values of the points that are actually away from the electric heater, right? So that is common sense, right? So now just consider the points T4, right? So T4 is very much closer to the electric heater, right? So the temperature at T4 must be definitely higher than the temperature at the point T3, because T3 is away from the electric heater, right? And if you're going to consider the temperature at the point T2, right, so in that case definitely temperature at the point T3 must be definitely higher than the temperature at T2, right? Because T2 is far more away from the electric heater when compared to the point T3, right? So I hope you can understand that. Okay, right. So now carefully focus the diagram, right? That is on your left hand side, right? So now there you can see the electric heater is placed at the top, right? So now if you are going to consider the temperature at the points T4, T3, T2 and T1, right? The temperature at T4, right? That means the temperature according to the point T4 is higher than the temperature according to the point T3, right? Because four thermocouples are placed uh, on the points as labeled by the notations T4, T3, T2 and T1, right? Now because if you're going to consider the point T4, T4 is very much closer to the electric heater, right? And T3 is very much closer to the electric heater with respect to T2, right? More than T2, T3 is very much closer to the electric heater or the heat source, right? So the temperature at T3 is higher than that of T2, right? And if you are going to consider for T1, the temperature at T2 is higher than the temperature of T1, right? Because T2 is very much closer to the electric heater when compared to the point T1, right? So now carefully focus, right? So on top, right, on top of the combined material, right, we have the electric heater, right? Electric heater is the major source, right, that provides the heat, right? And here at the bottom you can see there is a cooling water system, right? That means at the bottom there is a cooling water path in order to capture the heat that is actually passing through this combined material, right? Because we know that because of the electric heater that is placed at the top, right? So that electric heater provides some heat that passes through the combined material, right? So at the bottom we have introduced a cooling water system. That means generally cooling water system means we input water at room temperature to this equipment in order to capture the heat that is actually passing through the combined material, right? Okay, so as a result of capturing the heat, that is passing through the combined material, right, the final temperature of the water will increase, right? Okay. Now here you can see, right, the place that I am pointing from the mouse pointer, right, there is a some selector, right, something like a regulator, right? So from that regulator you can read the temperature at the desired point, whether it is T4, T3, T2 or T1, right? So you can turn this. In this practical we are going to use this electric heater that is placed at the top in order to provide the thermal energy to this combined material, right? So for that, first of all, we have to adjust or we have to set a suitable current by using the regulator that I am pointing from this mouse pointer over here, right? So first of all, the first thing that we have to do is we have to set the required value for the current in order for this electric heater to operate. So when measuring the temperatures, right, initially the temperature values for T4, T3, T2 and T1 will go on increasing, right? So before taking the final reading for the temperatures, right, we have to wait until the temperature readings will reach to a certain fixed value, right? So that fixed state, right, the state where the temperature values come to a stable value, we call it as the steady state, right? So the final temperature readings are taken only at the steady state. In this practical, there are two lines that carry water, right? So one line carries water into the separator, right? And the other line that carries water away from the separator, right? So now we know that we have provided some heat to this combined material from the top with the use of the electric heater, right? So now the heat, right, that passes through the combined material is actually given to the cooling water system, right, that we have attached at the end of the material, right, as indicated at the bottom, right? Okay. So now here we say that the entire heat that this combined material carries is given to the cooling water, right? So that means from one connection we give normal water at room temperature into this apparatus, right? And then what happens is that water captures the heat that passes through the combined material, right? And that water we take out from this material from a separate line, right? And also now here you can see, right, that I actually point from the mouse pointer there, right? So one thermometer that measures the water inlet temperature, right, into this apparatus, right? The other line, right, that measures the water outlet temperature after the combined material has released its heat to the cooling water system. So when performing this practical, right, so first of all we adjust the current, right, and we provide some heat from this electric heater in order to pass through this combined material, right? And when the steady state is reached, right, then we read the temperatures at the points T4, T3, T2 and T1, right? And also I have taught you that to this equipment we have provided two water lines, right? So one water input line that takes water at room temperature into the equipment, right? And the other water line is the water outlet line, right, that carries water after it has captured the heat from the combined material, right? Okay. So now here we have done something, right? So now if you consider that water outlet line, right, so to that water outlet line we have connected a valve in order to regulate the water outlet flow rate, right? So I have mentioned that to the water outlet line we have connected a valve, right, in order to adjust the water outlet flow rate, right? So now what happens is from the water inlet line we are providing water at room temperature into the equipment, right? And from water outlet line we are going to get the water, right, when the combined material has released its heat to the water, right? So now I want you to focus about the valve that we have connected to the water outlet line, right? So now if you are going to consider the take-in values, right, in the first attempt, right, so what we actually do is, right, after adjusting the current we provide some heat to the combined material from the electric heater, right? So then when the steady state is reached we are going to read all the temperatures, right? And then during the first attempt, right, we are not going to do any adjustment of that valve that is connected to the water outlet, because during the first attempt we allow, right, complete full flow rate from the water outlet valve, right? Because now you know that from the valve that we have connected to the water outlet line, right, we can regulate the outlet water flow rate, right, or the heated water flow rate, right? So then during the first attempt, right, we allow we completely allow the full flow rate, right? We completely allow the full flow from that water outlet line, right? So then that means, right, actually we are using that water outlet line in order to uh, pass that heated water away from the equipment, right? So now in the second attempt, right, in the second, when taking the second set of readings, right, what we are going to do is, right, so now I have already mentioned you that we have attached a valve to the to that water outlet line. So in the second attempt we adjust that valve, right, such that it will block the water outlet in the second attempt, right? So in the second attempt, when compared to the first attempt, right, we have blocked, not that doesn't mean we are completely going to block the water outlet, right? So in the second attempt we have actually blocked the water outlet when compared to the first attempt, right? So then in the second attempt, right, it takes higher amount of time, right, with respect to the first attempt in order to pass out the heated water away from the equipment. Now when we are going to take the readings for the very first attempt, right, we are going to operate the water outlet line at the fully open condition, right? So that means previously I have mentioned you that we have attached a regulator, or in other words we have attached a valve to the water outlet line in order to regulate the water outlet flow, right? Because we know that we give water at the room temperature to the equipment, right, and that water is going to capture the heat that is actually passing through this combined material, right? So that water is taken away from the water outlet line, right? So now at the very first attempt, right, we are going to operate the water outlet line at the fully open condition, right, without regulating that valve, right? Okay, in that manner we are going to measure the time taken to collect 200 milliliters of water from the water outlet line at the very first attempt, right? So that is the point, right? So now what we are going to do at the second attempt, right? So now in the second attempt, by using that regulator we have connected to the water outlet line. So now by using that regulator we are going to block the water outlet flow, right, by turning it, right? Okay, so now with respect to the previous scenario, now in the second attempt we have actually blocked the water outlet line, right? So now what will happen to the time taken in order to collect 200 milliliters of water? So now when considering the second attempt, time taken to collect 200 milliliters of water will increase with respect to the first attempt, right? Because the reason now you have blocked the water outlet, right, by using the regulating valve, right? Okay. So now you are going to go for the third attempt, right? So now in the third attempt, what you will do? In the third attempt, you will again block the water outlet line with respect to the second attempt, right? So now in the third attempt, time taken to collect 200 milliliters of water will increase with respect to the second attempt, right? Because now what is the reason? The reason is that now you have blocked the water outlet line. So now in the fourth attempt, you have blocked the water outlet line more than with respect to the amount that you have blocked in the third attempt, right? In the fourth attempt, time taken to collect 200 milliliters of water will increase with respect to the third attempt, right? Because what is the reason? Because now the reason is in the fourth attempt you have blocked the water outlet line more than the amount that you have blocked in the third attempt, right? So definitely the time taken to collect 200 milliliters of water in the fourth attempt will increase with respect to the third attempt, right? Right. So now I have some results for 5 different trials, right? See, trial number 1, 2, 3, 4 and 5, right? Okay. So now here you can very clearly see that time taken to collect 200 milliliters of water is 40 seconds, right? In trial number 2, it is 43 seconds, right? So now you know that in trial number 1, if you are going to consider that water outlet pipe, right, if you are going to consider that water outlet line, in the trial number 1, we are going to allow the full flow rate through the water outlet line, right? Because I have already told you that in that water outlet line, there is a regulating valve that we have connected to the water outlet line in order to regulate the water outlet flow, right? So in trial number 1, we are going to allow the full flow rate, right? And in trial number 2, what happens? In trial number 2, we are going to block the water outlet little bit when compared to the trial number 1, right? So the time taken to collect 200 milliliters of water in trial number 2 is little bit higher when compared to trial number 1, right? So that you can very clearly see from there. See, in trial number 3, time taken to collect 200 milliliters of water is higher in trial number 3 when compared to trial number 2, right? Okay. So like that, now we have values of 5 different trials. Agree? Right. So now the next thing, now see here, see what is this W1? W1 is the water inlet temperature into that apparatus, right? Because I have told you that to that apparatus we are giving water at room temperature, right? So that is the temperature W1, right? And now if you're going to consider W2, so what is W2? W2 is the temperature of water after capturing the heat from that combined material, right? Because we know that we have provided some heat to that combined material from the electric heater, right? So then what we are doing is, also I have told you that at the bottom we have connected a cooling water system in order to capture the heat from the combined material, right? So after capturing that heat, see, the final temperature of the water has increased, right? See, now what is the final temperature of water? It is 32.9, right? So like that, in trial number 2, 3, 4, like that. So we have measured the water outlet temperature in the respected trials, right? And what is T4? Now, if you're going to consider T4, what is T4? T4 is the temperature point that is very much closer to the electric heater, right? See, so because of that, the temperature T4 is greater than T3. And also you know that like T2 is below T3, right? So then temperature at T3 definitely must be higher than temperature at T2, right? Okay. Now here I want to tell you something, right? So actually these observations are taken from the thermal conductivity apparatus where the top material or the material that is having the highest thermal conductivity is copper. There are several types of equipments, right? So actually these results are taken from the thermal conductivity apparatus where the top material is copper, right? But in the explanation video, I have explained you by considering the top material as aluminium, right? Or I think you can remember the material that is at the top is aluminium in my explanation video, right? So here, what is the material with the highest thermal conductivity? That is copper, right? Actually, these readings are taken from that apparatus, right? Okay. So the material with the highest thermal conductivity is going to have a higher length, right? Okay. And the material with the lowest thermal conductivity is having a lower length, right? Okay. So that's the scenario, right? So that is what I want to tell, and actually I can tell you that, right? Actually, what is the length of the copper material? The length of the copper material is 50 millimeters, right? So it is having a higher length. The material at the bottom is stainless steel, right? LSS. So the length of that is 25 millimeters. But keep in mind, the diameter of both the specimens is. So now let's see how to do the calculations, right? So now we will do calculations for the trial number 1, right? Okay. So now here what is happening, right? The heat flow through the combined material, right? So let's write that. Actually the heat flow, right, through the combined material, right, is given to that cooling water system, right? Let's say that heat absorbed, right, by the cooling water system, right? Heat absorbed by the cooling water system, right? Okay. Right, because now there is a heat flow through the combined material, right? So that heat is captured by the cooling water system, right? Okay, fine. So now what is the heat flow through the combined material, right? So that is given by this equation. Let's consider now here there are two materials that are combined, right? See, on top we have copper material, right? This is copper, right? And after that we have SS, stainless steel material, right? Okay. So now let's do the calculations for the first material, that is copper, right? Okay. So now what is the heat flow through the first material, right? So that is given by K copper, that means thermal conductivity of copper, right, multiplied by cross sectional area, right, multiplied by temperature gradient, right, or the difference of the temperature at 2 points, right, because you know that there are 2 temperature points in each material, right. So now when you are going to consider it for copper, right, so we know that on the top position we have T4, which is having the highest temperature, so the temperature difference, right, so T4 minus T3, right, okay. Temperature gradient means the temperature difference divided by that length. So what is the difference between the 2 temperature points? Now here we have T4 temperature and here we have T3 temperature point, right. So the difference between the 2 temperature points for copper material is 50 millimeter, right, 50, let's call it L copper, right. And now here be very careful. Now here there are 2 different scenarios, right. So let me tell you that one is the length of the material, right. So if you are going to consider that material, that one is the length of that material, right, and length of the material and the difference between the 2 temperature points are 2 different scenarios. Be very, very careful, right, okay. So Ka delta T divided by L, okay, so that equals heat absorbed by the cooling water system. What is that? That is mass of cooling water system, mass Cw, mass of cooling water system, right, Mc. What is C? Specific heat capacity of water, Mc. Delta theta, what is delta theta? Temperature difference between, like the difference between the temperature after capturing the heat, that is W2 minus the water inlet temperature, that is W1, right, okay. Actually when applying this equation, actually we are talking about heat flow rate, right. So what is the Fourier equation? So see what is the Fourier equation. Let's focus the Fourier equation, Fourier, right. So now what is this equation? This equation is actually Q dot. What is Q dot? Q dot equals Q divided by T, right. That means heat flow rate, right. That means like heat per a specific time, right, okay. You understand that heat is measured in joules, right, and per unit time, joules per second means actually in watts, right, okay. So we know that Q dot equals Ka temperature difference, but here you have to put the temperature, here you have to put the highest temperature to the first position, right, because now generally difference means final minus initial, but here as according to the equation, here if you say T4 minus T3, T4 must be higher than just, right, the difference between the temperature points, right, we are going to take the temperature, right, so that is L. So this is the equation actually, right. Actually this is not just heat per a unit time, right. So this equation we are going to equate with Q divided by T for water, right. What is Q? Mc delta theta, we know that. So this is grade 7 equation, you know that, right, per unit time. Because now what is the reason? Because in this practical we are going to measure time taken to collect 200 milliliters of water, you know that, right. In this practical we are going to collect 200 milliliters of water, right. So what is mass of water then? Volume multiplied by density. C we know, specific heat capacity we know, delta theta we know, that is W2 minus W1. Time we know that time T is the time taken to collect 200 milliliters of water. So write it, right, for copper material, right, for copper material we can say K copper area, right. So what is the cross sectional area? That is pi d copper, that means diameter, cross sectional diameter of the copper material, phi d square divided by 4, right. Temperature difference for copper is T4 minus T3, right. Ka delta T divided by the length between the 2 temperature points, L copper, right, okay, equals volume of water, right, that means definitely 200 milliliters of water, right, that is okay, right. But Be very careful to apply in standard units, right? I will be doing such a kind of a calculation also, right? Multiplied by density of water, raw water, right? Into temperature difference of water, W2 minus W1, right? W2 minus W1. Be very careful. Divided by time taken, right? So now in this equation, you know all the values, right? So what is W2? That is the water outlet temperature. W1 is the water inlet temperature. And here mass, right? So here the mass is given by volume multiplied by the density, right? So what is the C? C is the specific heat capacity of water, right? So what are the units? So that is 4187 joules per kilograms per Kelvin, right? So, and what is the time? Time you know, right? Again, refer the observation sheet, right? So you know what is the time, right? Time you know, C you know, rho you know, V you know, W2, W1 you know, right? So this side you entirely. So now if you are going to consider the combined material, right? We know that in the combined material, the top portion is copper and the bottom portion is stainless steel, right? So now when applying that Fourier equation, right? So when you have to find the thermal conductivity of copper, then you have to consider the copper section only, right? Okay. So now here, see, now here we are using this Fourier equation, right? So that is the equation we are going to equate the values that you have evaluated from this equation, right? So that equals this one, right? So here this K1 stands for the thermal conductivity of copper that you actually need to find, right? So what is area? Area is that is the cross-sectional area of the combined material, right? Because now if you are going to consider the combined material, right? So both the materials are having the same cross-sectional diameter, so that means the same cross-sectional area, right? So that you know, that you can find, right? And what is the Fourier equation? You know Fourier equation, right? So what is that? K, which is the thermal conductivity, then cross-sectional area into temperature difference divided by the difference between the temperature points, right? So that you know, right? And here I want to tell you something, right? So if you are going to consider the combined material like that, right? Now here one thing is the length of the material, right? And the other one is the difference between the temperature points, right? But according to this practical, length of the material and the difference between the temperature points are considered as same, right? Okay. And you know that T4 and T3, right? T4, T3 belong to copper material, right? Because T4 is the one that is very much closer to the electric heater. You know that, right? Okay. So now that is the thing, right? And the entire heat that is passing through the combined material, right? The entire heat through this material is actually absorbed by the cooling water system, right? Okay. So now we know the heat absorbed by the cooling water system, and that we are going to equate with the heat flow through the combined material. But when you have to find the thermal conductivity of copper, at that time you are going to consider only this portion, right? So to this portion, so now when you are going to apply the Fourier equation for the copper material, right? So that equation will be K copper. This is the thermal conductivity of copper that you have to find, right? So that multiplied by the cross-sectional area, right? So how to find the cross-sectional area? If you know the cross-sectional diameter, you can find the cross-sectional area. So that is given by the formula pi d squared over 4, right? So what is the cross-sectional diameter of copper? That is 25 millimeters, right? Because the cross-sectional diameter will be same for the stainless steel material as well, right? Because it is a combined material, right? Okay. So now K cross-sectional area into the temperature difference for copper material, right? So if you're going to consider the temperature difference for the copper material, right? So you have to put it as T4 minus T3, right? Yeah, T4 is higher than T3 because T4 is very much closer to the electric heater, right? So divided by the distance between the temperature points, right? So what is the distance between the two temperature points, T4 and T3? So that is exactly same as the length of the copper material, right? So that will be L copper, that is 50 millimeters, right? Right? The distance between the temperature points for copper material is 50 millimeters, and the distance between the temperature points T2 and T1 for stainless steel material is that is 25 millimeters, right? So here also the distance between the temperature points for stainless steel material and the length of the stainless steel material, right? Both the parameters we consider as same, right? Based upon the dimensions, right? So then now this side you know, right? Because the length of the difference between the temperature points, you know, T4, T3, you know, right? If I just show you sample, so now what is T4 there? See, T4 you know, T3 you know, right? So now you can apply T4, T3, you can apply L, you know, diameter you know. So then this side you can equate with the heat absorbed by the cooling water system, right? You got it, right? So what is the next thing? Next thing also same, right? Because you know that the entire heat that is passing through the combined material is absorbed by the cooling water system, right? You know that, right? That is given by this equation, which is mc delta theta divided by time that we apply for cooling water, right? So that you can equate with. Now you are going to equate this with the Fourier equation for the stainless steel material, right? What is that? So that is K stainless steel cross sectional area of the stainless steel material, and the difference between the temperature points, or the difference between the temperatures for stainless steel material, that is T2 minus T1, right? Okay, you got it, right? So divided by the difference between the temperature points. What is that? That is L stainless steel, which is the difference between the temperature points is 25 millimeters, right? So you have to put all the values with the standard units, right? So then only you are getting the correct answer, right? That is the next most important thing. Be very careful to put all the values under the standard units, right? Okay.